Remember that there's no gain of electrons when electricity flows. For every electron that moves, another one takes its place, and it takes the place of another one. The cycle continues incredibly rapidly, so that electricity flows nearly at the speed of light, or at the speed of light. Right. So what this means is that the electricity has to flow somewhere, to somewhere, and from somewhere. When we have an electronics project, we have to talk about circuits, because we make projects where the the electrons just go around. And around and around. Because no electron is actually created or destroyed, and every single atom in the project needs to have the right number of electrons. They just continue to flow through. The outer valence electrons just continue to flow through the circuit. If energy could flow and it didn't have to flow through a circuit, then you'd eventually have incredibly negatively charged molecules and atoms, because they would just be gaining and gaining more and more electrons as time went on. Why this is important, I'll show you here. So I have a circuit that electronically connects. Let me explain what everything is first. I'm using wires that have a very low resistance in order to not mess with my project. I'm using a breadboard in order to easily connect my electronics together. A breadboard has small gaps that squeeze onto the metal pins and parts of your... Here, let me zoom in actually. Breadboards can electrically connect things because they squeeze onto your components, making it so that they are electrically connected. And in rows like this, they're all together. So there's electrical connectivity from this side of this light and this wire. And this wire connects electronically to this one, even though they're not touching, because there's little bits of metal in the breadboard. Over here, I have an Arduino. What I'm using this Arduino for is I've connected it to a wall outlet, and I'm using it to provide a regulated 3.3 volt power supply to this. That's the only reason why I have this. This is my power supply. It converts wall energy into the energy that I need to use for this, and I'll go over that some other time. Now, I've used red to signify positive power and black to signify negative power. This is just what most people do because it's the custom. Red is always voltage in, and black is always the connection to ground. Ground is always negative, and voltage in is always positive. That's just by definition. Now, electricity flows from here to here, then it flows through this little channel to this wire. This wire picks it up and connects it to the resistor. The resistor connects this wire to the LED. The LED takes the energy that it gets and turns on, and then that energy goes down and then back through the wire, then back to the power source. Now I'm going to show you that if I disconnect any one piece, the light will go off because no electricity will be flowing through it. As I pull that out, the light goes off. As I pull out the LED itself, the LED goes off. If I pulled out the resistor, the LED would go off. If I pull this out, the LED goes off. That's just to show you that it does in fact need to be electrically connected. There's a reason I have a resistor here. LEDs are weird. They have a voltage drop across them, which means that when you put in an LED into a system, on one side of the LED, the voltage will be, say, 3.3 in this case, and the other side, right after it, the voltage will be closer to, I believe, 0.8 for this green LED specifically. This is the schematic drawing that you use for an LED. Not important for you to know at this moment. So there's a drop in the voltage over an LED. However, you would think that since the voltage changed, the amperage would change, because remember, V equals IR. So when the voltage drops from 3.3 volts to 0.8, then IR must change too. So the resistance of the circuit must change, or the amperage of the circuit must change. The amperage must change, or the resistance must change. However, the resistance doesn't change across from here to here. And the current doesn't change. What that means is that LEDs will allow as many electrons as possible to flow through them. This can actually burn up the LED. Because we don't want to burn out our LEDs, and in fact I already burned out several of them, we use a resistor. A resistor has a voltage drop across it too. Let's go back here. That's the schematic drawing for a resistor, that or that, depending on who you're talking to. This resistor specifically has a resistance of I don't know how many ohms. Ohm symbol looks like that. I don't know how many this is. I just picked it out of my box and it worked. But because there's a resistance drop, and because for resistors V equals IR, the current is limited because of the resistor. Because the resistance stays the same, the voltage drops, therefore the current drops. It's kind of confusing as to why LEDs don't follow Ohm's law, because after all, it is a law of electricity. I don't know the answer offhand. It's just something that you can look up sometime. If I was using a tungsten coil, which is what a lot of light bulbs are, then it would have then it would regulate the amount of current flowing through it automatically. If I were powering this from a battery source, batteries have an internal resistance which would keep it from burning up that quickly. But let me show you what it looks like when it burns up, just to show you not to do it. And this is actually going to smell really bad soon. So I'm going to power this directly. It's much brighter. And is it burning up? I think it is. It's getting warm. Let me do this. Oh yeah, it's burning up. It's turning yellow. Let me do this. There we go. It's turning yellow, getting darker. The inside of it is breaking. It's getting dimmer and dimmer and dimmer. And come on, burn. I'm not sure if you can see it. Yeah, green LEDs are a lot hardier than red LEDs, apparently. Oh, it's flickering. It's flickering. Come on. Come on. It just won't burn. I've been thwarted by a green LED. So I can smell it burning. And it's hot. Oh. Let me see if this one will burn up. Nope. I can't find any of the red LEDs. Alright. I'm finding this hilarious. I cannot burn something for you to watch. Okay, so I'm going to use the same LED as before, but I'm going to power it from a higher voltage source, a larger voltage source. So this, remember, provides 7.2 volts. So I'm going to connect red to red. And zooming in again, see if you can see the smoke. black and red to red. Burn. It's really dim. Okay, so my attempts to burn these LEDs in front of you are sort of failing, so you can't see the smoke escape. Sorry about that. But anyways, this is now dead and will never be useful again. So it's gone. But the important thing to take from all of that is, once again, that you need the circuit to be completed, that you have loads, you have voltage equals IR, except in the case of LEDs and diodes. You have to regulate how much current is flowing through your parts, or else you'll break them. And depending on what your voltage is, your total amperage will go up. And that batteries have internal resistances. Let's talk about how electricity flows from positive to negative. Electricity flows from an area of high potential to an area of low potential. It flows from an area of high voltage to an area of low voltage. Now, why is this specifically important? It's important because when you're making your pieces, you have to understand how the electricity will be flowing through the system. In order to illustrate how it, sort of the idea of what's going on, the electricity moves from an area of high potential down to an area of low potential. I kind of like to think about it as water flowing down a hill. Instead of gravitational potential energy changing, however, it's electrical potential energy that changes. The important thing to notice is when it's going down, there has to be some form of change. The energy has to go somewhere. This is why you don't just connect batteries to themselves. If you were doing that, the energy would just be flowing through the system, but it wouldn't be going anywhere. And it's not like there's enough resistance in the circuit to cause enough friction to use it up. So instead, what happens is they get overcharged, basically. Since not enough of the energy is used up, it starts to build in here. It turns to heat energy, which gets hot really, really fast, even with the internal resistance of the batteries, which can melt the batteries and cause them to explode, burn things, etc. It's not good. You do not want to breach your own power cells. You can also pull things to a ground that is just bad, which will mean that there's energy flowing through your circuit normally, but then you make a bad connection to ground and everything will skip the rest of your circuit and just go straight to ground. It's important to understand that so that when you're actually building circuits, you don't start to wonder where all your energy is going if you've made an improper connection to ground from one of many ways. Just requires a little bit of wire in the wrong place. I'm getting a little bit too detailed here. Gonna stop this video, and next video is going to be about various electronic components and how we use them.